Bom dia a todos. Bom, meu nome é Silvia Lavagnoli, eu sou gerente de marketing da OpenCAD e já é tradição, muitos de vocês já sabem que os webinars da OpenCAD acontecem às quintas-feiras, mas hoje o nosso webinar é especial, pois nós temos aqui um convidado, o James Wiken, que é engenheiro de aplicação da MathWorks. Hoje é manutenção preditiva, aplicada à indústria aeroespacial e defesa. No entanto, trata-se de um assunto muito abrangente e por isso, se você atua em outro segmento, continua por aqui, pois a gente tem certeza de que você poderá aplicar esses ensinamentos de hoje na sua área de atuação. A apresentação será feita em inglês, mas vocês podem fazer perguntas em português, caso sintam-se mais à vontade, pois a gente tem a apresentação da OpenCAD, o Eloy Oliveira, alguns de vocês já devem conhecer, e ele vai responder as perguntas no quadro de questões, ok? James, welcome to this webinar organized by OpenCAD. I am sure your presentation will be very helpful for all our attendees. So I encourage all the attendees to ask questions in Portuguese or English in the board questions and have a webinar.
All right, yeah, thank you, Sylvia. So as I'm sure she mentioned, my name is James Wiken. I'm an application engineer for the MathWorks. Unfortunately, I don't speak Portuguese, but Sylvia does. So like she said, if you do have any questions, feel free to type them in the chat. If they're in English, I can read them and answer them directly. If they're in Portuguese, they can be translated for me. And that's fine too. So whichever you prefer. So today we're going to be talking about predictive maintenance with MATLAB. All right, so in this, we are going to be using data or models or a combination of the two in order to be able to know when our system or device or machine is going to fail, right? You might have seen videos like one that I would show here sometimes, but of like a wind turbine spinning out of control and eventually breaking apart. Or if you've ever been in an airport and you get that nice notification over the speakers saying our flight's been delayed due to mechanical issues, right? These are all situations where predictive maintenance could have been potentially helpful, right? Where we have these systems that cost millions of dollars either to produce or to operate, or both. And failures can be very dangerous or very, very expensive, right? Now, in certain situations like this one here with the wind turbine, maintenance itself can also be very expensive and dangerous, right? This is very tall. You can see this one is using essentially a crane and a lifter here to get somebody up there. In more remote locations, you might fly somebody on top of these things using a helicopter. So it's not the easiest thing in the world in order to actually do maintenance in the first place, right? So we want to look at using predictive maintenance as a way to make sure that things don't fail, but we kind of maintain it as optimally as possible, so we're not being wasteful in how we keep these things up and going. All right, so more broadly speaking, there's a few different types of maintenance here. Right, the first one is just a reactive approach, right? We're just going to wait till things fail, and once they fail, we'll replace them or we'll fix them. Right, an example of this is, if you're like me, you don't really replace your car battery until it fails, and so you just kind of wait, and then when the problem arises, you fix it. Right, now, there's some issues with this, obviously, right? Unexpected failures, especially for more complex or more important systems, can be really expensive and potentially dangerous, right? You can't really just wait for a jet engine to fail mid-flight. That's going to lead to some serious problems. Another approach, and one that's pretty widely used, is scheduled maintenance. Okay, so we're just going to do maintenance at a regular rate. Like, so for instance, you might change your car's oil every 5 or 10,000 miles, depending on the oil of the car. For once again, turning to the aircraft example, every so many flights, you just bring it down for maintenance no matter what. Okay, now this can be helpful, right? Because it helps eliminate failures before they occur, but because it's just kind of at a regular rate and not really responding to the individual situation, uh, it can end up causing us to do a lot more maintenance than might be necessary, and there's no guarantee that it's going to actually eliminate all failures, right? We use some experience and some knowledge of the system to find some threshold to or some rate to do that maintenance at, but it doesn't really respond to you know the real world happening. So what we're going to look to do is we're going to use predictive maintenance in order to try to find some nice balance between these reactive and skeletal, right? We don't want things to fail, but we also don't want to do extra maintenance, and we want to really make sure that we don't miss things that might fail earlier than we might normally expect them to. Okay, now there's already some examples of predictive maintenance out there. There's certain car models that forecast problems with particular components like the battery, the fuel pump, or starter motor. You'd see that like a light would show up in the dash of your car, telling you that a problem is going to occur or might occur soon. Uh, that sort of thing can be for predictive maintenance, but the main challenge here, and the one that we're going to be addressing today, is that it's often difficult to you know be able to forecast when those problems are going to arise, especially for more complex equipment. Okay, so how do we go about doing that? What sort of data do we need? What sort of modeling do we need in order to be able to make those predictions? Because once we can, then we can decide how to respond. Okay, so at a high level, what exactly does a predictive maintenance algorithm do? Okay, well, there's a couple of different uh, things that it can do, and it really comes down to a couple of questions you might want answers to, right? So more generally speaking, predictive maintenance is a form of machine learning. More generally, it's a form of AI, and in this, we're generally going to take data that we have and want to make a decision based on the data we have. And I mentioned before, there's a couple of questions that we probably want answers to in this process. Okay, so with predictive maintenance specifically, a couple of questions we would ask are things like, what's the current condition of my machine? When will my machine fail? If my machine has failed already, then I might be asking, why did my machine fail? Right, but we're trying to stay on the predictive side of it. So these are kind of our two main questions, right? What's my current condition? So I can then decide what to do based on that. And do I have any sense of how long I have until failure is going to occur? Okay, so this top one, what's the current condition? This is often referred to as condition monitoring. Okay, so this is a process where we're going to take data from sensors generally on our machine, and we're going to use that in order to be able to determine any significant changes or trends that are manifesting in our system that can point towards failure or at least degradation happening with our device. The second one, when is my machine going to fail? That is often referred to as predictive maintenance or prognostics, or more specifically, remaining useful life or time to failure estimation. And that's really where we're going to take that same sensor data, and we're going to take some historical amount of that sensor data, and we're going to build a model that can predict when maintenance needs to be performed. Right? It's not just what's the current condition of my machine; it's how long, specifically, how long in time do I have until my system's going to fail, so that I can decide when to bring it down for maintenance. Okay, so what does this look like? Right, so there are some examples of this. This one here is a company called Safran. They make jet engines. It's going to be pretty similar to the example we're going to be going through today. But they use our tools in order to build out a health monitoring system. Right, so this is more of the condition monitoring side of it. Right, so this is what's the current condition of my machine. But they're able to monitor their system, use the sensor data they have in order to be able to predict failure indicators. They can then extend that into actually predicting the time to maintenance as well. And what this allows them to do is it really improves aircraft availability, right? If I know when my engines are going to fail, before they fail, then we don't have that, oh, we're delayed for mechanical issues, right? Those mechanical issues have been sorted out before the flight is boarding. It also reduces maintenance costs because we're not just kind of doing maintenance on things that don't really need it, and so we can really focus our efforts where they're best used. And in order to develop out the system, we start on the desktop doing data analysis, working with that data, building up models, things like that. We can then take the models that we construct, compile them, share them out into a wider range, and then eventually deploy them all the way out into enterprise level integration for use with maintenance and service teams and across their industry. If you're interested in seeing this presentation in more detail, there's a link here where you can find it. But we're going to be solving a kind of similar problem, all right? So we're going to be starting with a pretty standard prognostics data set provided by NASA that is sensor data that's coming off of a bunch of engines of the same model. You can see this turbofan here. And we're going to use that sensor data to answer those two questions, right? What's the current condition of my machine? How long do I have until failure occurs, right? We're going to start with the first one because it's a pretty standard way to approach this, starting with that condition monitoring, getting a sense of the current health of my machine. That sort of stuff is very useful when we move into the actual remaining useful life estimation. So we'll start on the condition monitoring side and then move into the predictive maintenance as we go along. But we're going to be following this sort of standard workflow right here. We're going to be importing the data in. We're going to be training the model so that we can predict when failures occur, or so we can know the current health. And then the second half of this we're not going to be doing too much today, but you would then deploy it out to actually work on the live sensor data and make it useful in the real world. Okay, now I've said we'll build a model, we'll build a model, we'll build a model, right? I've said it a few times. There's a lot of options when we're talking about building a model. And they'll fall somewhere on the spectrum here, right? On the far left, this is just first principles modeling. So this is all, writing equations in order to sort of approximate the real world, sort of stuff you'd see in like a physics class, things like that. And on the far right is a purely data-driven approach, right? Where we're not really using equations, we're going to be using machine learning techniques or deep learning techniques in order to build out some sort of estimation of the system based on those structures. Now, there are different options kind of in between here as well, parametric models, things like that. And we, MATLAB and Simulink, we have tools for across this entire spectrum. As the title of this presentation might have suggested, if you read at the beginning that predictive maintenance, a data-based approach, you can kind of guess which end of the spectrum we're working in today. We're going to be on this far right side. We're going to be using machine learning techniques in order to tackle this problem today. But it's not to say that you can't use some of these others as part of the process as well. All right, so let's actually dive into the problem. Okay, so our first example, we're going to be doing that condition monitoring, like I said. Now, I want to set out a few sort of assumptions that we're going to be working with. First thing is that we may or may not have failure data recorded, right? Think about these sorts of systems. We really don't want things like jet engines to fail. So capturing failure data in the real world is very difficult, right? And we don't want it to happen. So there's no guarantee that we even have failure data to begin with. Okay. The collection of this data is going to be used with an existing maintenance scheme already. In this case, it's a scheduled maintenance. We bring it down every however many flights, excuse me. And so we're going to have to work with that. Now, excuse me. All right. So in this particular example, we're performing that scheduled maintenance often enough that no failures have occurred, right? So we're kind of setting it up to be a little bit more difficult here. We do have some information that the maintenance crews can give us to tell us which engines could have ran for longer or which ones really need to be ran for maintenance when they were. So we can use that insight to help justify the models that we're making. All right, so can we use this data, even though it doesn't include failure information, to be smarter about how we schedule the maintenance? Okay, So let's hop into MATLAB and we'll start solving this particular problem. All right. So first thing we need to do is we need to load in our data set. All right, so I've loaded it in here before. This is currently contained in a number of CSV files. You can see they're all here. I'll open one up in Excel really quick, just so we can get a quick kind of high-level look at it. This is for one particular engine. The time here is for each flight, so this is a cycle up and down. And then we've got essentially like an averaged value of each of these different sensors for that particular flight, right? So we're seeing things like temperature, pressure, speed, fan speed, bleed, things like that, right? Some pretty standard stuff when it comes to a jet engine, right? So we're going to use these various sensor values in order to try to see if there's evolution over time and if we can detect degradation in the system, right? And that's what we see here when we've loaded it in, right? Those same values or same sensor readings. Now, first thing we need to do, right? We can look at what we have, but really we want to get a sense of, is there any sort of change? Is there any sort of trend that we can pull out of these sensor values? Because if they just kind of stay flat or if they're very noisy throughout, then it's going to be very difficult to see if they evolve over time, right? So looking here, we can see that there's some trends that are developing in a few of these, right? This one goes up, this one goes down, this one goes up as well. This one maybe is a little less useful, right? Because it's just kind of noisy. There is a general downward trend, but the noise might outweigh that trend, right? So we are seeing some strong trends in some of these sensors, right? So that's good, right? This is the sort of stuff that we need to see in our data, because if we're looking for degradation over time or we're looking for change in behavior over time, then our sensor values or the features we're using in order to detect that, need to show it. Okay, now this is just looking at one particular engine, right? We'll look at a more macro scale of this with multiple engines in a bit. But looking at these sorts of things where you see, oh, okay, they kind of change over time. Couldn't I just do something like a control chart where I've got, upper and lower control limits on this and say that it goes outside that limit for some amount of time, say like 5 in a row. And then if it does, then I just kind of flag it, right? And that's a fair kind of idea, but there's a couple of issues with it, right? It involves you setting that threshold manually as part of this process. You could use some statistics and things like that to determine what that might be. But the other thing is that right now, this control chart is limited to looking at just one of our sensors, right? This particular one is the low pressure compressor outlet temperature. Okay, we have what, 17 sensors that we could use, and so this is kind of really limiting the amount of data that we're using for this sort of analysis, right? So this is, keep this sort of stuff in mind because we'll kind of build on this, but we're going to need to kind of change our techniques so that we can take advantage of the full breadth of data we have available to us. Okay, so we're going to go back to our data, and this time, instead of loading in just the one file for engine number one, we're going to load in all 100. Okay, so to do this, we set up something called a data store, point it in the folder that's containing all of our data, and then create a tall array out of that. So this is just loading in all those files and concatenating them together because they have the same structure, and storing them in one big table. The tall array is there for if that data is too big to fit into memory, which in predictive maintenance it often can be. And so this just makes it really easy to scale to whatever size the data is without to change how the algorithm is implemented. Okay. Now we are going to introduce one of our assumptions here. I said before, we're assuming that maintenance is being done at a regularly scheduled rate. So in this case, we're going to say that anything over 125 cycles, we're just going to assume that we did the maintenance and cut off everything after that. Okay. Okay, so let's do what we did with the one engine and start visualizing some of these sensors. Okay, so this is plotting basically a sample of our total data, but it gives us a sense of, if some of those trends we saw in the singular image or singular engine also show up in all 100 of our engines. Okay, so we're seeing some of the same stuff, right? We're seeing this go down, this go up, this go up, right? In this one, we're not necessarily seeing a change in mean, but we are seeing a change in variance, right? That kind of the spread kind of grows over the life cycle of the system. So that's still potentially useful, right? But at the end of the day, we are seeing that there are some sort of discernible trends that are manifesting in these different sensors, right? So that is a good sign that these could be potentially helpful for us. Now, one thing you might notice is the scales of these different sensors, right? And it really just comes down to how these things are measured and what units we use when we gather it. But we're seeing things like the pressure is on the order of like 50, right? Whereas the fan speed is on the order of like thousands. Okay, now when we start to want to use these together, if we just kind of left it as is, the fan speed would kind of outweigh any sort of influence that something like the outlet pressure might have just by virtue of having a bigger number. So to fix that, we're just going to standardize our data, right? This is a really standard thing in machine learning techniques, but all we're going to do is we're just going to center each of our signals on 0 and scale them so that they're range of -1 to +1. Right, this just makes it so everything starts off at an even footing, and 1 doesn't dominate just because the units that is used to define it happen to be larger. Okay, so once we do that, we are going to, well, I guess, once we do that, we got everything on even footing, and we did that because we want to look at these things in sort of combination with each other. Right now, we're visualizing them all kind of separately because there's so many of them, and it's difficult to make in this case, a 9-dimensional graph, right? So in order to really be able to do further analysis, what we're going to look to do is something called dimensionality reduction. Okay, this is because it's hard to visualize, it's kind of hard to understand those higher dimensional representations of a system. And so if we can collapse it down to something like 2 or 3 dimensions, then suddenly a whole suite of visualization opens up to us, right? All of our standard plotting routines, all that sort of stuff is available to us even in, even for these more complex systems. There's several ways that you can do this sort of dimensionality reduction, but one of the most common ones is something called principal component analysis, or PCA. Okay, essentially, if you haven't heard of PCA before, sorry, skip through this. If you haven't heard of PCA before, essentially the idea is, we have various values that are measured along sort of arbitrary axes, right? They're measured along axes that we could define, right? The pressure, the temperature, and so on. Now, one issue with this is that the variance or the spread of the data, or for our purposes, the information doesn't necessarily align with those axes that we were able to measure along. And so if we want to be able to capture a lot of that information, but be able to use a fewer number of axes to represent it, then what we can do is we can essentially just rotate so that our axes line up with that spread, right? And so if we take our first axis, or our first principal component, so that it lines up with the greatest variance of the data here, that's our first principal component. Okay, and then we repeat that process with with all of our others, and keeping these principal components orthogonal with each other. And what this lets us do is, once we've done this sort of rotation so the axes line up with the spread of the data, then we can just look at the first couple of principal components and still see most of the information, right, and cut out everything else. Okay, We'll see that in practice in a second here. All right, so we'll do principal component analysis by calling this PCA function. And then we can take a look at this visualization here. And I said, we're doing this so we can capture most of the information or most of the variance with just a couple of axes. And so this kind of shows that numerically. Okay, so the orange here is the individual components information that it captured. The blue is the cumulative if we take that principal component and everything before it. Okay, so the first principal component, right, the one that's aligned with the greatest spread of variance, captures about 75% of the variance or 35% of the information contained within our data, which is huge, right? With just two, we capture nearly 90, and then from there on, it kind of drops off pretty significantly, right? Each one only contributes 1-ish percent or less to it. Okay, so what that ends up meaning is with just two principal components or two features, we can explain 90-ish percent of the information contained within the system. That we started with 10 plus sensors or 10 plus features, right? So this is pretty powerful, right? Because it allows us to take that very high dimensional system that we had before and represent it in a much more manageable and low dimensional way, so that it makes it a lot easier to visualize and work with it and so on. Okay, so we're going to take those first two principal components, and that's what we're going to be working with kind of going forward. Now, let's take a quick look at what these principal components look like. Okay, so this is just the first principal component on the x-axis and the second one on the y. Okay, we can see in this sort of scattered bin plot, you think this is like a 2D histogram, the majority of our data is sort of clustered in this rectangle here. Okay, and it's a little faint, so depending on your monitor, you may or may not see it, but there are sort of these two arms that reach out to the right and up and to the right. Okay, so that's what this looks like, and that's good, right? We want to be there. We want there to be some sort of discernible shape in this system, right? My guess would be, and we'll test this going forward, is that this sort of cluster of most of our points here, that's going to be where like normal operation is, or at least where we start, right? Because for the majority of the operation of the systems, they should be in normal operation. So I would expect the majority of my points to be there. And then perhaps as as it degrades, maybe it moves out along these kind of two arms out here. Right. Well, like I said, we'll test this. We'll check it. That's part of this process. But that's kind of my starting hypothesis on this by looking at this. Now, let's take a quick look at the third and fourth principal components. This is just kind of a sanity check here to make sure that we're not missing anything by kind of discarding these. And we can see here, this is sort of a zero-centered normal distribution with not much variance, right? So this is essentially what you'd refer to as like noise, right, or white noise here. So not really much information to be gathered here. So this kind of verifies, or at least makes me feel better about getting rid of all those higher principal components, because there's, like I said, we're looking for some sort of discernible shape here, and having that sort of just zero-centered normal doesn't really tell me much. All right, so when we do this, right, when we move to these principal components, we do lose the sense of like, they don't really correspond to a specific physical value, right? You can't say, oh, principal component 1 is the temperature, right? It is a combination of all of our sensors, right? A weighted combination of all of our sensors. And we can look and see what that combination is right here. So you can pull that right out of the principal components. It's not hidden or a secret or anything like that. And generally what we're looking for here is just like the magnitude. Okay, so we can see in our first principal component, everything actually contributes pretty evenly here. Moving into our second principal component, we can see some of them start to drop off in magnitude, right? These ones are starting to get like an order of magnitude lower than everything else. So these ones kind of contribute less to that second principal component. So this at least lets us know, are the sensors we're using useful? If one was very low magnitude in both of those, I could probably just not include that to begin with, and so this could be a good way to kind of pare down the sensors that I know are important or not. Um, if I'm using this sort of analysis. Okay, so let's sort of repeat the plotting stuff that we were doing before, but this time we're going to use our principal components as opposed to the direct sensor values. And we're just going to pull out a sample here, and we'll start visualizing some of these systems. Oh, interesting. Let me run this. All right, so the first thing we're going to do is we're going to visualize the first and last points of our engine, right? We want to see if there's any sort of shift from the beginning of operation to the end of operation, right? We're looking to see that movement or that degradation happen. And so that's where we'll start. So we'll pull these out and we'll do a quick visualization here. And here we go. All right, so the blue is the first points, the red is the last points. And if we remember what that, I kind of draw what we saw for the overall principal components before, right? We had that sort of rectangle in the bottom left, and then two arms kind of going out this direction. Okay, and we're kind of seeing this here as well, right? We're seeing everything starts in this sort of rectangle down here, and it kind of spreads up and to the right, some more than others, as things go on. And this is kind of what we'd expect, right? This is why we're looking at predictive maintenance, because some of these things are moving quite a bit out, right? Which could point to degradation happening, right? It could mean that these ones out here might need maintenance more. We still have to test that and see if that's the case. But we're also seeing that there's a number of these things that end up pretty close to where they started. And these might be situations where they're being brought down for maintenance too early. Okay, but we're starting to get a sense of the shape of things, see how things evolve, see these regions of normality versus moving closer to degradation or failure. This is what we're trying to do here. Now, I said that we need to test this, right? We need to test to see, hey, are these ones that are really far out, are these actually the problematic engines? Okay, so I did say before that we have some information from our service techs, and we can ask them, hey, which ones were the worst off, right? Which ones needed to be brought down for maintenance? And so they told us these four engines here, 39, 57, 70, and 91. So we'll just highlight the last 10 cycles of those particular engines. And we can see here that they're the ones that are the farthest out from this, very dense region of points here. So that helps, right? That kind of help prove out the thoughts we're having, right? Where it's going to start in this corner here, and then as it degrades, it either moves to the right or up and to the right, right? This sort of separation here, right, where we've got kind of one behavior up top and one behavior down below, right? This might be pointing to two different methods of failure, two different sources of failure. We're not going to really get into that today, but it might be something to explore as we go through this. And we can even track a path of one of these engines um, through this process. So let's run this. And hopefully you guys can see this animation going. but this kind of starts over in the rectangle, and then over time it drifts farther and farther out, right? And this is one of those problematic engines, right? So with all this information, we can set some initial criteria for how we want to sort of divide up this space, okay? We are going to, this might look a little arbitrary, but it's sort of chosen in order to put a certain number of points in each of these regions, right? So the green region, this is sort of normal operation. This is where everything starts, and this captures around 90.5% of the overall data that we have, all right? The orange region, this is where it's starting to move towards degradation, but doesn't have imminent failure yet. And this captures, along with the green, 99.5% of our data. And then the last 0.5%, this is capturing the farthest outreaches, and these ones include those 4 engines that were shown to be closest to failure, right? Nothing has ever failed in this, so far. That's not to say that wouldn't, but now what we can do is at any given time, we can take the sensor values off of a flight and then plot it in this space and have it tell us, is it a normal operation? Is it in this sort of warning operation, and is it in this red, right? And then we can start forming a policy on this, right? We can say, if it's in green, we don't worry about it. It's good. Does it go over 125 flights? It's fine. It's in green. Is it in orange? Okay, maybe after 5 flights in orange, we bring it down, right? Let's try to be conservative. We don't want, we really don't want this stuff to fail. And so say something like that. And then for whatever reason, it gets all the way to red in that cycle. As soon as we see it's red, it's being brought down for maintenance for the next cycle, right? But the idea is that we capture most things in this orange space, so it never even gets out into the red. Okay, now, as I was describing that, we kind of used a couple of different machine learning techniques here. It may not feel that way because we didn't ever train a model. But what we did here was something called unsupervised learning. And coming back here, if you're not as familiar with machine learning, it's kind of divided into these 2 big sections, unsupervised and supervised. Supervised learning is probably what you're familiar with if you touch machine learning before. It's where you have input and output data and you're building out a predictive model. Things like classification, regression, that sort of stuff falls into here. Supervised learning is where we don't have any output data, right? So in this case, we don't know what failure looks like because it was always brought down for maintenance before failure occurred. And so all we can really do is try to group and interpret and understand the trends in the data. And so that's what we were really going for here, right? We were looking at the data, trying to find a good way to represent it, to be able to visualize it, be able to understand what's going on, and then be able to make some of these groupings here so that we can actually act on the information that we have. Now, the point at which we could take this and move into the supervised approaches, now that we have these regions, we essentially have labels, right? We have an output. We have green, we have orange, we have red. And we can take this, this set, we can now apply those labels, and we could, proceed to make a classification model where, we take that data, we do the classification, and then you would basically send the new data in to our model, and it would tell us whether it's in the green, red, or yellow. If you want to see how you would do that, there is this classification script. So when we send out all the code afterwards, feel free to look through this, and it will kind of walk you through the process of how you build out one of these models, how you validate it, and see how well it performs. Right. Now, having this model, having that representation that we built, right? The whole reason that we do that is so that we can utilize that information to our advantage. Okay, so this is one particular example of what we might do with that information, right? So here's our current state: 125 flights, everything gets brought down no matter what. But now that we have this condition monitoring system, we can say push it out farther, right? Let's push it out to 135 flights. If it's in the orange for say 3 flights here, we'll bring it down. Otherwise, we'll bring it down when it gets to 135. This allows us to collect more data, allows us to collect data over a longer time span, so we might see more of that degradation happen, we might see more manifest, but it also helps us build up confidence in our system, right? If we continue to not have failures occur, but are able to bring some things down earlier, but have most things go down much later, that's already helpful. And so we can repeat this process. Okay, we're more comfortable with our model, we validated it, we've seen that it works well. Let's push all the way out to 150. We're still going to bring things down early if they show up in the orange for 3 cycles in a row. But now some of our systems can stay out for 150, right? And if we push this out even farther, we might get to the point where every single one of our engines is being brought down based on our model, as opposed to some arbitrary limit. Now, you might have some arbitrary limit that you need to follow just because of government restrictions or certain requirements of the industry, but at least this lets you push it out farther or closer to that limit, while still having the the kind of the peace of mind of you're tracking, that you have some confidence in whether these things are going to fail or not. But if you are able to push it out so that everything is being determined by the model, that is a sort of primitive predictive maintenance algorithm, right? We're not able to predict how long we have until it fails, but we are able to react to this sort of thing before the failure occurs and bring it down accordingly. All right. So one good example of this is one of our customers called Mondi. They're a manufacturer of plastic and paper, and they built out a condition monitoring system very similar to what we just described. If you look at these pictures down in the corner, these should look kind of familiar, right? And they're able to monitor the current conditions of machines and just bring them down when they're needed, rather than just arbitrarily. And they're expecting huge savings when full production is set up, and they're able to very quickly build out a prototype in MATLAB and be able to deploy it out into production very quickly. Once again, if you're interested in this, there's some links to the user stories that you can follow when you get the slides. In addition to this, they were able to build out an app and some graphical tools to help with the visualization and using this system as well. Okay, so that was condition monitoring. I'm gonna stop for a second, look to see if there are any questions. I don't see any.
No questions so far. No, right. No questions so far.
Sounds good. All right, so let's move into the remaining useful life estimation, right? We talked about how we could answer what's the current condition of my machine. One potential way we could answer that. Let's try to answer the second question. How long do I have until my machine fails, right? So we're going to use pretty similar data to what we had before. We're going to expand out, right? We're going to use 200 engines this time instead of 100. And in this example, or in this sort of scenario, we're going to have some combination of sensor data from our equipment, known failure thresholds, so we have some sense of what failure might look like, and or runtime to failure of similar equipment, right? So we know how long something lasted before it failed. Okay, now we're going to take advantage of what we did before, right? We can use condition monitoring to determine when the system starts degrading, and then once it starts degrading, then we can use this remaining useful life estimator in order to say, okay, it's starting to degrade. How long do I have until that degradation turns into failure? Okay, so that's what we're trying to predict. Now, coming back to this overview of machine learning, we are going to be going to the supervised learning approach here, and specifically, we are going to be looking at regression because we're trying to estimate a numerical value, right? A number of cycles or a number of days or a number of minutes or what have you, whatever your time scale ends up being. Now, there's a number of different methods that we can use in order to solve this sort of problem, and really it comes down to what data we have available to us at the time in order to be able to solve our problem. Okay, so let's say that we have a system and it starts in an optimal state, right? It's either brand new or just got off of maintenance and so on. And it has some lifetime that it can run until failure occurs, okay? Now, we have different opportunities to gather data in this process, okay? So let's say that we don't have any sensors, right? And we're just recording how long the system lasts until it failed, okay? This is still a potential way that we can do this without sensors at all. It does require a very high volume of devices in order to be able to do this, but we can use that lifetime data and something called the survival method in order to try to build a model to predict how long something else might survive. We can include things like operating conditions and stuff as well in order to try to add some more information to that system too. But let's say we do have some sensor data, right? Not necessarily for the entire life cycle. We could use that in combination with some known failure thresholds that we might get from experience or simulation or modeling, and use something called degradation methods. And then the last one, and the one that we'll be using today, is for a system where we had sensors on it the entire time. So we're able to capture data all the way from start to failure, and we don't really have a good sense of what failure looks like or a specific threshold that we can say, yes, when it passes this, that's what failure is. And so in that case, we're going to use something called similarity methods. And like I said, this is what we're going to be using in our example today. This is another view of this, just kind of broken out to more specific ones. And just so you're aware, this is the particular one we'll be using in a second, this residual similarity model where we have run to failure history with some known degradation dynamics. So we know if it degrades linearly or exponentially or so on. All right. So let's hop back into MATLAB and we will start tackling this problem. Oh, at the bottom here for some reason. All right, let me zoom in a little bit just so it's a little easier to read. Okay, so first things first, we're going to load in our data. Now, this data is stored in a slightly different way. Actually, let me clean up our last time. All right. So our data here is stored in a slightly different structure as before. Before we just kind of had one big table where everything was kind of there wasn't any sort of distinction between the runs other than just like a value that told us that it was, engine 1 versus 2 versus 3. In this one, we're storing it so that each lifetime is its own separate time series here. Right? So we've got time series for engine number 1, engine number 2, and so on. And you can note that these are not identical in length, and I wouldn't expect them to be, right? Not all systems last exactly the same amount of time, and we're not arbitrarily bringing them down in this case. We're letting them run all the way to failure in this particular situation, right? So we're going to do the same thing that we did before, right? We're going to visualize this data. We need to understand what we're working with, and we have even more sensors this time. We have 21 sensors that we're pulling from. And, before we did this sort of just visually where we plotted that and we looked to see if there was change over time and things like that. This time we're going to do it numerically. Essentially, we're fitting these all to a linear model and then just calculating the slope out of that model and pulling up the things with the highest slope, right? The most change over time, because those contain the most amount of information for us, right? So these are the top three here: the low pressure turbine output temperature, the static high pressure compressor outlet pressure, and the bypass ratio. These have the greatest slope over the life cycle of these systems. Okay. So this is the same thing that we did before. We just did it visually before, where we looked to see if trends existed. This time we're doing it numerically and just pulling out a subset of them. Okay. Now, the big difference here between what we did last time and this time is for our dimensionality reduction, instead of doing PCA, we're going to form what's called a health indicator. Okay. Now, the health indicator is just a value that tells me what the current health of the system is. We're going to assume that it starts at 1 and failure occurs at 0, right? So it ranges from 1 to 0 and it will degrade in some way between those two values. In this particular case, we're just going to assume that it degrades linearly, but you can choose, a different degradation if it made more sense, right? If it degraded exponentially or quadratically or so on, right? So here's our ideal health indicator, right? This isn't based on any of our sensors or anything like that. Really, the only thing it's based on is we know that it starts at 1 and it fails at 0. Now, we're going to take this ideal health indicator and we're going to estimate it based on our actual sensor data that we have, right? And this is what's called making a fused health indicator, right? So there's a number of ways we can do this. We're going to do a really simple one here. We're just going to fit a linear model based on those sensors that we pulled out, those 3 kind of top ones, and as our input data, and then our output data being that ideal health indicator we had. Okay, so that is training it, doing the fusion, and this is what it looks like right here. Okay, so these are our fused health indicators. Now, we still have the assumption that it starts at 1, but there's no guarantee here that it is actually going to go all the way down to 0, right? This is the estimate based on the sensors we have. You can see this doesn't even look that linear. That's still fine. We just kind of need it to be consistent. Now, you may be thinking, couldn't you just stretch it so that it goes down to 0 to keep that sort of assumption we made in the beginning? You could, but what that ends up doing is it ends up really changing the shape of these curves for sort of the worse. And the curve shape here is really what we care about, because when we get into the actual modeling here, we're going to be comparing time series curves to these existing ones that we have here. Right, so we're not going to stretch it down to 0. That's kind of counterproductive in this particular case. Okay, so this is our, this is the input to our model, right? This fused health indicator, right? This is kind of similar idea to that PCA that we did before, right? Where we're taking that high dimensional system and collapsing it down into a lower dimensionality representation for both visualization and modeling in this case. So we're going to build out this residual similarity model here. Now, if you are familiar with CANN models, it's a very similar idea where it has a number of nearest neighbors that it's comparing to, but instead of comparing to specific points, this model compares to other time series instead, right? So we're comparing to other curves. Now you might be thinking, carrying these entire time series along would be very heavy, right? Because we're storing all that data, and as we get to larger and larger data, that becomes very difficult to do. What this actually does is it actually stores a sort of parameterized curve fit of those curves, right? So in this case, we're saying it's a second order polynomial. We're just storing those parameters in the model to kind of keep it at a manageable size. Okay, so train the model there. I kind of skipped through the training because it's not too important. We just kind of fed it the data that we had through doing that fused health indicator. What I really care about is the actual evaluation of the model, because I think it does a good job explaining how it works and what it does. So let me bring up this animation here, and we'll see this model in action. So typically we wouldn't be running the model this early because we would be relying on our condition monitoring system, right, to tell us when we start to move into degradation. But we can start running it at the beginning of it too here. But we can see in this top right, the red line, this is the current time series, or the engine that's currently running. And you can see it's kind of growing over time. Now, as it goes, it selects the 50 nearest time series to it, and then fits this histogram in the bottom and makes an estimation accordingly of how long it's going to have until it fails. Up here, we can see the green line is the actual time to failure. The red is the prediction, and then the bounds, the 90% confidence intervals around it. And we can see here that we're ending up converging pretty close to the actual value, but the biggest thing here is how long beforehand we were able to make that prediction, right? So 60 cycles before failure, we had a pretty good estimate for how long we had until failure, right? This is near exact. And like I mentioned before, this whole region up here where we weren't very sure, we probably wouldn't be running this model in the first place, right? We would be relying on our condition monitoring system to tell us when we start to move into degradation, which would probably happen around like here-ish, maybe, where our, where our answer is converged to reality, or converged a lot closer to reality. Right, so this is a situation where it's worked well. Let's run this again, but this time it's going to be with a system with an engine that has a bit different behavior. So once again, at this point, we probably wouldn't be running this model. We'd be waiting on the condition monitoring system to tell us when it's moved into that sort of warning space. But we can see here that we are severely under predicting for our system right now. Okay, we'll see why in a second, but I want you to watch the plot in the upper right, that red line. Now, right now it is tracking very similar to any other one of those green ones that it's tracking with, right? But here we hit this sort of cusp, right, where it's going to bounce back up. Ooh, wrong way. It's going to bounce back up here, right? And as this evolves over time, we can see that it kind of continues up there. Now, the model's responded, right? It's changing the green ones, up to those ones up top, right? Because now those are a bit more representative of it. So we're getting a little closer, over here in our estimate, but still not quite right. And this continues to evolve. If we kept watching this, it would kind of go out up and to the right, over here. It's like, or this way, right? Now, this is kind of pointing out the limitation of this particular model, right? This model, like most machine learning models, really only knows what it's seen before. Okay, and so if we give it a time series that looks very different from anything it's seen before, then it's going to kind of struggle to give a good estimate with it. Now, the nice thing about these models, though, is that they're not static, right? They can be improved over time. So as you get more data, as you get situations like this where the model doesn't work well, you can include this in your training set for the next time around and build out a better, more robust model as it goes over time. So, situations where it's worked quite well, where it kind of follows normal behavior, but these ones are a bit more out there, can run into situations where the model isn't able to converge as well. Now, in this case, it's not too bad because it ends up being that we'd bring it down for maintenance a lot earlier than we would want, which isn't ideal, but at least the system isn't failing. And like I said, you would use this with an existing condition monitoring system and things of that nature too, as backups to the process. All right. So that's about all I have for you. One thing to mention here is that we mostly just talked about how we would go about building these sorts of models today. Know that the next step would then be taking them and putting them out where they're actually going to be used, right? So MATLAB has a number of different deployment tools to help with that process. So if you want to deploy them out as, say, an executable or some sort of software library, or deploy them out onto some sort of enterprise or cloud system, then we have tools to support that: MATLAB compiler, compiler SDK, and production server. For models that are deployed out on, say, edge devices, say like a microcontroller or something like that, you can also take some of these models and generate code for them in the form of C, C++, or some other low-level languages, so that they can be deployed out in the out on the devices that they're doing their maintenance for, their condition monitoring for. Right? As for MathWorks services, I don't know what OpenCADs are specifically. I don't know if they want to talk about any services they provide on this or any support they do. So I'll give Sylvia the option to do that in a second. But just a few key takeaways what we talked about, right? So both maintenance and failures are potential cost and risk in a lot of different industries. So we want you to be able to use MATLAB in order to build out these sort of predictive maintenance systems that can help prevent or minimize both those things, the cost and the risk, right? And so the predictive maintenance in particular, right, is a strong tool to be able to do this sort of stuff. And for both of what we talked about, the condition monitoring and the remaining useful life estimation. If you are interested in the specific tools we use today, we used a mix of the stats and machine learning toolbox, which is kind of what we used for the first example, and then the predictive maintenance toolbox for the second one. And if you're interested in learning more on the predictive maintenance, I would definitely suggest going here in the predictive maintenance toolbox documentation. There's the getting started section here with a number of different tutorials and videos to help you start the process, as well as a whole suite of full workflow examples all along the process that you can use as starting points or as references for your own particular problems. And some of these use MATLAB, some of these use Simulink for the modeling part of it, but these are extremely helpful on getting started. Sylvia, I don't know if you had anything you wanted to say here.
Hi, James. We have a question here.
Okay.
We have a question asking if the plots are just from MLX, MLX, or can be generated by scripts.
The plots we did here?
Explain about the live? Yeah. They are interested in the animated plots. How the animated plots are generated, just from the live script, or we can generate it from the scripts?
You can generate it from either. Yeah, that's not something that's unique to the live scripts. So I was running this plot engine data function down here. So this is just running a for loop where it's updating the plots as it goes through with the new data point. So when you get all the code, you can take a look at this to see how it was done. This is kind of one way you might do it, but you can do it with a normal script or a live editor. Either would work.
Okay, thank you. I think that is all the questions. No, we have one more question. Which skills in the statistics or stochastic models do you need to have for using this toolbox?
What skills do you need for it?
Yeah.
Okay, yeah. So there's a few things that can be helpful for it. So the predictive maintenance toolbox actually is built on a few other tools. The stats and machine learning toolbox is kind of the main one. Being able to do the dimensionality reduction or being able to use some of those machine learning techniques can be quite helpful. But it also is built on the signal processing toolbox and the system identification toolbox. Those two tools can be used for different methods of feature extraction. We didn't really talk about that too much today because we were just using sensor data directly, But a pretty common thing you would have to do in this is doing something called feature extraction or feature creation, where essentially it's right here where you're building up things called, more generally called features, but they can also be called condition indicators in here, where you take sort of the raw sensory data you have and do some mix of stats, signal processing, maybe sysid, in order to turn those into features that are more useful for the actual model itself. So knowing a bit about feature design and things of that nature can be helpful. There are some tools in here to help with that process. Something called the Diagnostic Feature Designer can really help with the creation and exploration of those features. And then, once you have that, the modeling part of it is fairly straightforward. It really comes down to kind of choosing the model that you need to use based on the data you have. And then I guess the other skill that you might want in that is knowing how to be able to validate those sorts of models. But the validation process is kind of similar to what you would do in any other machine learning model. So it's a long answer, but I would say the things that are most helpful are knowing how to do feature extraction design, and then knowing how to do validation and testing of a machine learning model once you have it, right? The other thing that could be useful is being able to model your system, because as I said before, sometimes gathering failure data can be very difficult or expensive. So simulation can be a good way to generate that sort of data to be able to be used for these models.
Okay, thank you. That's all the questions today.
All right.
Thank you.
Sounds good. All right, well, thank you for attending. Like I said, make sure to send out the slides and the code that was showed today, as well as a couple of scripts that I didn't show. There's one on doing that classification model, which is kind of extension to the first one we did. And there's also one that shows how you can use deep learning to solve very similar problems as well. So you can take a look at that one too. And I believe if you need tools or trials for any of these things, you can reach out to OpenCAD for support in doing that. Great. I don't know if Sylvia is still here. She has anything she wants to say at the end. But not. Thanks for attending.
Thank you for the audience. Thank you, James. Thank you for all. Have a good day. Obrigado a todos os atendentes. Fiquem atentos aos canais do OpenCAD.